If you have watched any sci-fi movie that involves time travel or warp speed, you have probably heard the term time dilation. It sounds like something only theoretical, something that only happens near fictional black holes or at impossible speeds. But time dilation is real. It is a fundamental feature of our universe, and it is happening right now, just not always in the dramatic way that Hollywood likes to show you. We are told that nothing is faster than the speed of light. That is the cosmic speed limit, absolute and unbreakable. But there is a second, equally absolute limit in the cosmos that controls how we experience time, and that limit is gravity. The journey to understanding how gravity and time are linked starts with Albert Einstein. His general relativity theory changed everything we knew about the universe. Before Einstein, Isaac Newton saw gravity as a force, an attraction between two masses that acted instantly across space. But Einstein showed that gravity is not a force pulling things together. Gravity is a distortion, a curve in space and time itself. To picture this, imagine space-time as a huge, flat sheet. If you put an object with mass like our Sun on that sheet, it creates a dent. That dent is what we call gravity. When a planet moves near the Sun, it is not being pulled by an invisible force. It is simply following the shortest, straightest path possible through the curved dent that the Sun has made in space. This concept means that if you have enough mass packed into a small area, you create an immensely deep gravitational well. This curve in space is so strong it affects everything, even light, which has to travel through the bent, warped space. But here is where things get truly mind-bending. That sheet that gets warped is not just space, it is space-time. This means that mass warps not only distance, but also time. Time is the fourth dimension, and gravity slows it down. This idea leads us to the core question: why gravity slows time? When you are close to a massive object, you are deeper inside that gravitational well, or the dent in space-time. To an observer far away, time must compensate for the intense curvature of space. It is easier to think of the entire framework of space-time trying to maintain consistency across the universe. If light must travel a certain path through warped space, time must slow down so that light speed remains constant for everyone watching. This is why gravity slows time. The presence of mass creates a gravitational potential, and this potential changes the rate at which clocks tick. The stronger the gravity, the greater the curve in space-time, and the slower time runs. This effect is minute in our everyday lives, but it is entirely measurable. In fact, if we look around, we see that scientists regularly rely on the predictions of general relativity because of this effect, especially when dealing with satellites and space travel. If we do not account for time being different in high-gravity situations, our most accurate technology simply fails. The idea that gravity warps time isn't just theory for physicists playing with equations. It's an engineering problem that affects technology you probably use every day. To understand why GPS satellites literally have to correct for time dilation, we need to appreciate just how accurate these systems must be. GPS, or the Global Positioning System, relies on a network of satellites orbiting Earth. Your phone receives signals from at least 4 satellites to figure out your exact location. For the system to work accurately, the time it takes for the signal to travel from the satellite to your phone must be measured with extreme precision. Since these signals travel at the speed of light, even the slightest error in time measurement can throw off the calculated distance by hundreds of yards. These satellites orbit roughly 12,500 miles above Earth. This altitude creates 2 separate, conflicting time dilation issues that must be corrected constantly. First, there is the time dilation caused by gravity, a result of Einstein's general relativity. The GPS satellites are further away from Earth's center than we are on the ground. This means they are in a slightly weaker gravitational field. Since less gravity means time runs faster, clocks on the GPS satellites tick slightly faster than clocks on Earth. This small difference must be corrected for, or the satellites would quickly fall out of sync with ground clocks. Second, there is time dilation caused by speed, a result of Einstein's special relativity. The satellites are traveling at immense speeds around 8,700 miles per hour. According to special relativity, the faster an object moves relative to an observer, the slower time passes for that object. Therefore, the speed of the satellites causes their clocks to run slightly slower than clocks on Earth. the satellite's faster speed tries to slow time, but the weaker gravity experienced at that altitude tries to speed time up. The effect from the reduced gravity is actually much stronger than the effect from the high speed. So to ensure the GPS system works, engineers have to program the clocks on the satellites to tick slower before they even leave Earth. The clocks are set slower by roughly 38 microseconds per day, a tiny amount of time, but enough that if left uncorrected, GPS systems would be useless within hours. This is direct proof of time dilation in action. Every time you use GPS to find your location, you are relying on the fundamental principles of why gravity slows time. The failure to account for the warping of space-time caused by gravity means the entire system would fail, demonstrating that time is not absolute, but changes based on where you are in a gravitational field. When we move from the relatively gentle gravity of Earth to the extreme physics of stellar corpses, the effects on time become astronomical. Stars far more massive than our Sun end their lives in violent explosions, leaving behind incredibly dense remnants like neutron stars or black holes. Let us look at what happens to time near a black hole versus a neutron star. Both objects are tiny, yet contain masses far exceeding our Sun, creating gravitational fields strong enough to profoundly warp space-time. A neutron star is born when a massive star collapses, creating an object typically about 12 miles across, packing more mass than the Sun into a space the size of a city. Since a neutron star has a physical surface, a solid boundary made of pure nuclear matter, anything that falls toward it eventually collides with that surface. This impact releases massive amounts of energy. For accreting neutron stars, the infalling energy is radiated upon impact, making them incredibly bright, sometimes up to 100 times brighter than accreting black holes. Near a neutron star, the gravity is intense, and time runs significantly slower than it does on Earth. However, because it has a surface, there is still a point where infalling matter stops, and the extreme time warping is contained outside the object. A black hole, on the other hand, is defined by the event horizon, the point of no return where escape velocity reaches the speed of light. The black hole has no surface where matter stops. When matter crosses the event horizon, it continues falling toward the center and its energy is swallowed. This difference is crucial for time. To an outside observer watching an object fall toward a black hole, time for that object appears to slow dramatically the closer it gets to the event horizon. As the object approaches the horizon, the external observer sees time run so slowly that it appears to stop exactly at the edge. The light from the object is stretched out, redshifted by the gravity, making the object appear dimmer until it finally fades to invisibility, seemingly frozen at the boundary. This contrast in what happens to energy and time is key. One neutron star. Time slows down significantly near its surface, but the boundary is physical, and gravity allows observers to watch the object collide and release energy. 2. Black hole. Time slows down so dramatically at the event horizon that, to an external observer, the object never seems to cross. It just freezes and disappears. The object's energy is not radiated from a surface upon impact, but is captured forever. This leads us directly to explore what frozen time actually means, and what it doesn't. The bizarre experience of time near a black hole depends entirely on your point of view. When thinking about time stopping near a black hole, we must remember that reality is defined by the observer. What frozen time actually means, and what it doesn't, hinges on whether you are falling into the black hole or watching from a distance. To the outside observer, time appears to freeze right at the event horizon. This is because the gravitational field is so powerful that light emitted by the falling object takes progressively longer to escape, eventually taking an infinite amount of time to reach the external observer. The light gets stretched to lower and lower energies, making the object dim and appear stuck forever at the edge of the void. This visual freezing is a direct prediction of relativity. However, for the object or astronaut who is actually falling, time does not stop at all. The falling observer would feel completely normal as they cross the boundary. Their own clock continues to tick normally. They would not feel a sudden stop or a change in the laws of physics right at the event horizon. This is because the event horizon is not a physical surface like the crust of a planet. It is merely a mathematical boundary in space-time. An astronaut would simply pass through the point of no return, unaware of the cosmic drama unfolding from the perspective of the distant observer. So, frozen time means that to the external universe, anything that falls into a black hole becomes stuck at the boundary for eternity. But to the object itself, its existence continues, and time flows normally until it reaches the singularity at the center. Inside the event horizon, the warping of space-time becomes absolute. According to the diagrams used by physicists to map this extreme environment, the roles of space and time actually switch. The singularity, where all the black hole's mass is concentrated, becomes not a location in space that you can avoid, but a moment in time specifically, the end of time for anything that has fallen in. Every path taken by the falling object leads inevitably to that single moment. This intense distortion of space-time is why black holes force us to question the fundamentals of time and space. The singularity itself is a point of infinite density where our current physics breaks down. This leads naturally to the theoretical question of whether time can truly, absolutely stop anywhere in the universe, beyond just appearing to stop from an outside viewpoint. The most profound question regarding time and gravity is whether time could fully stop anywhere in the universe. As we have established, to an external viewer, time appears to stop at the event horizon of a black hole. But for the falling object, time continues until it reaches the singularity, which acts as the end of time. However, the laws of physics prohibit an absolute, objective halt of time for any observer in the physical universe, even at the singularity. If time truly stopped, all motion and change would cease. Even the most extreme effects we observe, like time dilation near black holes or the slowing effects on satellites, are relative. They describe time running faster or slower compared to another reference point. The key limit is the singularity. General relativity predicts that the black hole's mass collapses to an infinitely dense point where physics fails. This mathematical infinity suggests that our current theories are incomplete. Many theorists suspect that quantum effects, if properly integrated into the theory of gravity, would prevent this point of infinite density, or soften the singularity. If this quantum gravity theory were complete, the absolute halt predicted by classical relativity would likely be replaced by something less extreme, but still beyond our current comprehension. The search for a true quantum theory of gravity, often called the Holy Grail of theoretical physics, is driven precisely by the need to resolve the paradoxes created by black holes, including the singularity. Until that unified theory exists, we must rely on the understanding that time is always flowing, even if at an extraordinarily slow pace in strong gravitational fields. Let us step back and appreciate why gravity slows time across the cosmos, tying our local experience back to the galactic scale. The massive objects that populate the universe, stars, galaxies, and black holes, are constantly generating and shaping space-time. The presence of energy, including the strong electromagnetic fields swirling around active galactic nuclei AGN, contributes to the curvature of space-time. This is evident even when we observe the largest objects. For instance, the supermassive black hole at the center of the Milky Way, Sagittarius A, affects the orbits of stars millions of miles away. While we are far enough away, 25,000 light-years, not to feel its extreme gravity, the motions of nearby stars clearly show that an object weighing 4 million solar masses is packed into a small area. If time did not slow in this region, all of the physics governing those orbits would break. Similarly, astrophysical jets shooting out of black holes are driven by the tremendous warping of space-time and the twisting of magnetic fields near the core. The magnetic field lines twist into a cone shape due to the black hole's rotation, channeling and accelerating charged particles from the accretion disk. This rotation actually drags space around the black hole, an effect known as frame dragging. The sheer complexity and speed of these focused outflows demonstrate that the distortion of time and space is integral to the most energetic events in the universe. The universal concept is that time is intertwined with space, and their geometry determines reality. Without factoring in this distortion, as shown by the need to correct GPS signals or the behavior of stellar orbits, our measurements of the universe would be wildly inaccurate. This constant, intricate relationship between mass, space-time, and the flow of existence is the silent mechanism that powers everything from navigation systems to the most violent cosmic phenomena. The relationship between time and gravity introduces one of the most significant and confusing problems in physics, the information paradox. This paradox arises when we try to connect the physics of gravity with the physics of the very small, quantum theory. In general relativity, a black hole is a one-way street. Once something crosses the event horizon, it is supposedly gone forever into the singularity. The information, all the data describing the object's identity, mass, and energy is seemingly lost or erased. However, quantum theory proposes that black holes are not perfectly cold and dead. Stephen Hawking theorized that black holes slowly radiate energy, known as Hawking radiation, and eventually evaporate completely. This radiation is generated by quantum mechanical processes near the event horizon. Since this radiation carries energy away, the black hole shrinks over billions of years until it disappears. The paradox is this: physics states that information must be conserved. It cannot be destroyed. If a complex object falls in and the black hole later evaporates, leaving behind only featureless radiation, where did the original information go? If the black hole destroys information, one of the most fundamental laws of nature is violated. The current view among physicists is that black holes do not erase information. Instead, the information about what fell in must somehow be preserved and stored within the escaping radiation. The proposed mechanism for this preservation is still a frontier of research, but the implications are massive. Many believe that solving this paradox will require a theory where space and time are not fundamental elements of reality, but instead emerge from a deeper, more basic structure, possibly quantum entanglement. This means that the biggest mystery regarding time breaking near gravity is not just how it warps, but what time truly is at its most basic level. The black hole, through the information paradox, forces us to address these fundamental questions about the nature of existence. When professional astronomers consider these phenomena, what astronomers actually worry about tends to shift from the theoretical to the measurable effects that confirm general relativity in extreme environments. Astronomers rely heavily on observing the orbital periods of stars and other objects in binary systems that include black holes or neutron stars. They track the precise motion of stars near the galactic center to prove the existence of massive black holes. These measurements work only because the time-warping effects of gravity are consistent and predictable, allowing them to calculate the mass of the invisible object. Furthermore, astronomers are deeply focused on gravitational waves, ripples in space-time predicted by Einstein. Gravitational waves are produced when massive objects like black holes merge. These waves are oscillations of the fabric of space-time itself. When gravitational waves pass by, they cause space to stretch and squeeze. This process includes time speeding up and slowing down locally. The direct detection of gravitational waves by facilities like LIGO provides dynamic proof of the strong field effects of gravity, precisely the regime where time is most severely distorted. These events allow scientists to observe how space and time behave under the most violent conditions, revealing data about mass, spin, and dynamics. Ultimately, the goal is to observe black holes close enough to fully map the geometry of space-time, including the slowing of time and the dragging of space into whirling motion. Future instruments like the Laser Interferometer Space Antenna, LISA, aim to observe gravitational waves from giant black holes, merging and measure how the waves encode a full map of space-time geometry. If that map shows deviations from Einstein's theory, it could provide the first observational clue to a deeper theory of gravity, the ultimate surprise that could resolve the information paradox and define what time truly is. We have traveled from the gentle time distortion affecting everyday technology to the chaotic gravity that consumes stars and warps the fabric of existence. We confirmed that gravity slows time because mass curves space-time, requiring time to adjust so that the universal speed limit of light remains constant for everyone. This effect is so real that GPS satellites must constantly correct their clocks to account for the difference in gravitational fields between orbit and Earth. Near a stellar remnant, the fate of time depends on the object's nature. A neutron star has a surface that infalling matter impacts, whereas a black hole possesses a non-physical event horizon where time appears to freeze for an outside observer. For the falling object, this frozen time is an illusion. Their clock keeps running until they reach the singularity. If you want to understand space like a NASA-level analyst, quick without studying for years or paying thousands for a university degree, we have a community that will help you. Link is below. As to whether time could fully stop anywhere in the universe, classical physics points to the singularity as the end of time. However, the search for a quantum theory of gravity suggests that the singularity might not be an absolute halt, but a point where our current understanding fails. This search is driven by the information paradox, which forces us to ask if space and time themselves are fundamental. The most exciting progress in this realm comes from observation, where astronomers listen for gravitational waves, ripples in space-time that prove that time speeds up and slows down dynamically across the universe. To truly grasp the chaos and extreme nature of space-time, you need to picture what happens right up to the point where time begins to break. Click here to learn what happens inside a black hole.